Okay. Hopefully you enjoy some coffee. It's time to get back to business. So, Adrien, keep going.
Yeah. Right, so like what we've been doing this morning is like a bit of background on filtering using in a sequential context, and we have been seeing prefix filtering for like the general state-space model, which is kind of like an abstract object, and it's two kind of implementable instances, which are Gaussian and finite state space, right? What we're going to be seeing now, for like maybe 15 minutes, is the smoothing counterpart, which is actually fairly simpler because it only requires you to be able to compute the backward kernel and like express the backward kernel rather than like express the filtering update that appears in the forward pass. So rather than like looking at Markov kernels and their normalizing constants, so like having some kind of weighted Chapman-Kolmogorov, here we just consider the Markov kernel itself, right? So, and that's going to be that's actually going to be the backward version of the Markov kernel arising in the smoothing distribution. When you have that, it's really like immediate to see that this is associated. Okay. Everybody's convinced that that operator is associated. Yeah, cool. And the reason is like if you marginalize one step, then another one, then it doesn't really matter when you're doing it. Right. So once you have that operator, you just need to kind of like trace the Markov kernel you're going to apply that to, right? And so you phrase it like that. So you say, this is like the, where's my mouse? Okay. So let us define the reverse time Markov kernel that corresponds to what would appear in the backward sampling step of a particle filter. Right? So you are looking at your distribution at xt, given all the data that had been observed up to time t, and the following step xt plus 1. Okay. Okay, and if you remember well, that's exactly what appears in the sequential counterpart when we were doing the backward sampling, or just even the marginal. Yeah. So that can be expressed in the finite state space case and the Gaussian case, right? So you just say, okay, well, I know in the Gaussian case, for instance, right? I know for a fact that my joint distribution is Gaussian. Therefore, my conditional has to be Gaussian, and all I have to do is find the parameters, right? And that's just like a bit of linear algebra, and you get there. In the finite state space, you get the same thing. You just know the filtering distribution. Yeah, so like I'm assuming that we know the filtering distributions, right? Because they appear in the computation of those elements. Okay, so we have like pre-computed them using the prefix or the sequential case. So I know the filtering distribution at time t, and then I just need to compute the reversed transition matrices that correspond to going backwards in time, right? The operators, yeah, the operators, it's right. So it's just like the integral. You can just write it down for the finite state space. It's just a sum, right? And in the Gaussian case, you're just like composing Gaussian kernels, which corresponds to like affine transformations to Gaussians. So it's something you can compute. Saying like I didn't really have too much space to do that. The sampling case, right, is actually fairly easy. And the reason being that if my disappeared. But if my Gaussian element is n of if my Gaussian backup kernel is given by something like this, GT and LT, right? This is also essentially just ET X T plus 1 GT plus key of some standard Gaussian. All right. And so the only thing I need to do to be able to do sampling is to pre-sample those people. Right. So I just like sample Gaussians, apply the less key on it, and now I have a parameterization of my sampling distribution rather than a parameterization of my marginal distribution. Okay. And so once I've done that, I'm able to also like use essentially the same operators, so the Chapman-Kolmogorov, but instead of marginalizing, I'm just like applying. So instead of integrating, right, now I just keep track of everything that happened in the past. Yeah, and now I have sampled. That's something I added very recently. So that's essentially like the 2 seconds answer to the question, which I added.
So I still don't understand that. So I completely believe it's possible to do, right? But that seems like, won't that just give you samples from a marginal distribution of each type of, rather than from the actual full joint smoothing distribution?
Nah, so like the thing is, you assume that you have a sample for x plus 1, right? So like the last time step, I think we agree this is like a proper sample.
Yeah.
And the last time step, when you do the cumulative sum, it's not going to be changed. Right? So instead of thinking prefix sum, you can just think like sequential because it doesn't matter. What's happening? So I sample xt, right, which is Gaussian with a given mean and covariance. Okay, I sampled that. Now I assume I have pre-sampled, so I've computed my elements, right? And I have pre-sampled my Gaussian, which is epsilon t minus 1. Okay, and I know that xt minus 1 is just t minus 1 x t minus 1 plus t minus 1 and square root of t minus 1 or t minus 1, right? I'm just going to like apply that sequentially backwards. Okay, and the only thing you need to be aware of is like you have pre-computed those elements, right? And you just have pre-sampled the Gaussians, right? And so if you in terms of thinking parallel, because like it's associative anyway, you just think like I'm applying a cumulative sum on pre-sampled Gaussians. Yeah? Okay. Anyone confused by that?
Yeah, right. Yeah.
Yeah. Yeah, so actually, like it's something fairly useful to remember. To remember is that if you are being confused by the fact it's parallel and you have prefix sums, you can think the math in terms of sequential, right? Because it's associative, so it doesn't matter in which order you're applying the operations. So if it's easier for you to think sequential, do it, right? When deriving the math, like proving that stuff actually is correct.
Maybe you'll say this, I think I was just a bit confused by one thing you said. So if you want to compute all of the smoothing distributions and you have this sort of parallel framework set up, is it still the case that you need to build all of the filtering distributions for first and then come back?
Yeah.
Okay.
So it appears in the finite state space, right? You see it here.
Yes. Okay.
The Gaussian case, it's just because you see like So it's just that P of st plus 1, sorry, st plus 1 point that T is proportional to xt plus 1 xt and then P of right, so the feedback distribution is here. Okay, so yes. So yeah, like to do the smoothing, I mean, like there's no magic. You have to do the filtering first. Filtering, you gather all the filtering results, and then you reuse them in order to define your elements. That's the only thing that appears. That's the only place where they appear. They just appear in where you define the elements. Okay. Right. So it's actually exactly the same example, just like we just put both together. But so we saw the filtering case. So we saw the filtering case here, right? So with weird solving and doing stuff to be efficient, and then like the actual filtering was making the elements, right, and then applying the associative scan or prefix sum to the filtering operator and the elements you have defined. So that was it. The smoothing is essentially the same thing. So you define your smoothing elements, so E, G, L, which just like, I mean, they just pop out as soon as you do the Gaussian algebra magic, right? And you define your elements, your operator, which essentially correspond to applying an affine function to a Gaussian, right? And once you do that, same thing. The smoother takes now, to answer Sam's question, it takes the filtering and the filtering covariances, makes the associative elements based on the filtering means and covariances you have pre-computed, and then applies the prefix to that. All right. And that's basically it. It's actually really easy to do, right? You just need to be kind of careful that you're applying the inverse in the right place and making sure that you're not like swapping two matrices, because it's not commutative. But beside that, like it's very easy. Okay. Well, that's not where we were. Okay, so that's it for like exact filtering, right? So it's the cases, like it's basically the two cases where we have a solution that we can implement and we know it's going to give us the exact solution to our problem, right? And so now, like, I mean, we all like work on models that are specifically rarely Gaussian or rarely like just finite database models. And so how can we use all those things within the context of approximate or exact inference when we are thinking of Monte Carlo? Okay. So a fairly natural thing to try and do is to say, I have a space-based model. It's been given to me by my friendly applied statistician. And what would be the best linear Gaussian approximate of it, so that I would be able to then apply the exact Gaussian method on the approximation. Okay. When I say best, I typically mean KL divergence, and I'm just going to point to the fact that those KL approximations do exist, but they are a bit hard to explain. And so I'm going to go and do the next best thing, which is the Laplace approximation. Okay, so instead of going for like pure variational approximation of the state-based model, let's just like look at a Laplace approximate, right? So specifically, let's look at conditionally Gaussian models. right? So some things or some models where you have additive noise essentially, right? Like nonlinear transition, additive noise that appears, for instance, in SDEs, right? Fairly naturally. And let's try to find the maximum a posteriori. So if you just write it down, it's kind of long to write down, right? But if you want to find the maximum a posteriori, you look at your log density and you say, let's maximize that, right? Now, if you look at it closely, you realize it's a least square. Yeah? It's a weighted least square. Okay? And so you just write it like that. You just write it as such. You say, I build a matrix M, which is my covariances being stacked, or inverse covariances being stacked together. And then I build a vector V, which is just the difference between the time step xt and the f of xt minus 1, but also the observation and h of xt. Is it h? Yeah, but h. Right? And now I am actually like pretty convinced that this is indeed a least square problem. Yep. Anyone does not see it? No? Okay. Excellent. So if I have a least square, then I can apply any optimization technique, like quadratic friendly optimization technique I want, right? In particular, a standard one is the Gauss-Newton. Okay, so I have a current guess for my maximum a posteriori. So essentially a trajectory. Okay, and I'm going to find the next best approximate for the trajectory as the minimum of that specific loss function. Okay, or at least that's what I want to do. That's the Gauss-Newton method, right? So you look at it closely and you say, oh, bit hard, right? Let's just take the gradient. So you do that. You take the gradient, right? And you are looking at, sorry, no, you don't take the gradient, my bad. You don't do that. You just like, you already have the gradient. Gradient of V is there. So you now look at it closely, and so you just unwrap the Gauss-Newton objective. So we went from least square, we put Gauss-Newton, we unwrap it, right? And when we unwrap it, we realize that finding the maximum of the density, same as finding the maximum of the log density, right? Which corresponds, sorry, finding the next iteration of the Gauss-Newton corresponds to finding the maximum of a log density, which is a linear Gaussian state space model taken as the linearized version of what we originally had around the current guess. It's a bit convoluted. At least like I explained it in the convoluted fashion. Sorry about that. But you say, you essentially say, I want to solve the least square. I'm writing the Gauss-Newton, right? I look at the Gauss-Newton. I realize it's a linear Gaussian state space model, which I want to find the maximum a posteriori of. And the map of a Gaussian is its mean, right? And so all I have to do is to find out the posterior mean of a linear Gaussian state space model. And what have we been doing this morning? Well, we've been doing exactly that, right? Finding the mean and the covariance, because we've been trying to compute the marginal smoothing distribution, right? And also sample from the posterior. But here, like this corresponds to the marginal, right? And so this gives you an algorithm, which essentially says, I am going to compute the smoothing distribution of my linear Gaussian approximation. So I linearize the state space model around the trajectory. I compute the smoothing mean of that specific linear state space model, and I do that again, right? And that's basically it. So you start from an initial case, yes, whatever you want. You linearize everybody. You run your Kalman filter, your Kalman smoother, and you obtain the mean that you use as the next linearization trajectory, and then you just keep the covariance to be able to get like the Hessian of your Laplace approximation, right? Which is just like the inverse of the, well, minus the inverse of the covariance. Okay, and so you at least like, you don't have the actual Laplace approximation, but what you end up having is a block diagonal approximation of your Hessian. Okay, and then you can also sample from the Laplace approximation if you want. All good? Dong is making faces.
A little bit strange, but not strange, but a little bit as trying to get an approximation where you have the diagonal, like components are unrelated and correlated.
So the what is unrelated?
Like half components, but we are the elements of diagonal are 0.
Elements of the diagonal are 0. What do you mean?
Off the diagonal.
Of the diagonal? No, it's not. So no, it is not, right? Because like it's not because I give you the marginal covariances of the splitting distribution that the actual posterior does not have a full diagonal, right? Yeah. So once you converge and you have like something stable here, you can just linearize around that and take a sample, right? But it's just that the problem with state space models is you would end up immediately with the covariance of that size, right? You can actually express it. In fact, it's really easy to express the precision matrix, right? But it's a bit of a pain. So yeah, so it's not because it's not because you get the marginal covariance for free that is all you get. Yeah. So the KL approximations, they essentially work roughly similarly, except that you don't linearize using you don't linearize using Taylor, right? But you linearize using statistical methods. So you try and like get the best Gaussian approximation in terms of KL locally everywhere, and that typically requires using Monte Carlo or sigma points, any kind of sample-based approximation of your covariance engine. Okay, so again, it might look a bit painful. So here, like, it's not really a notebook I'm going to be showing, but so end to end, right? Once you have coded all your primitives, which is Kalman filtering, Kalman smoothing, so once you have coded all your filtering and the smoothing primitive functions, so like the associative scan or like the loop, what you end up doing is like, what you end up doing is you end up coding a fixed point, right? So you iterate a filter then smoother function on your current, what we call nominal trajectory, because this is a general method, but just think like the current best guess of your map, right? Then like you're gonna linearize your transition model and your observation around the nominal trajectory. I'll show you in a second, and then you just like kind of iterate until convergence. Okay, so again, like it's once you have all the primitives coded, then like it's five lines of code, right? And then like the so filter smoother. That's filtering here. That's like filtering parallel, for instance. Okay, let's go there. And so what you end up doing is you just take your minimal trajectory, in that case just our mean, right? And then you just create your parameters by linearizing, what is it here? Linearizing your transition mode, right? So I get my transition matrix, my covariance matrix, and my offset by just the Taylor expansion in our case. Same for the observation matrices, right? And I just then apply exactly what we have been seeing. So these are just the parameters that appear in the parallel version of the Kalman filter. Okay, so it's not that hard in the end. And then like you also have guarantees because it's a Gauss-Newton. You know that it's going to converge if you don't start it too far from the actual solution, right? Yeah. Okay. Any questions on that?
For arbitrary model, you can use that. And like when you SMC, you use the proposal you get on that.
Yes, some people have been using iterated Kalman as a proposer in SMC. Yeah, there are like a bunch of, I mean, they're like more in the electrical engineering realm, right? So you would have that in the transaction of ESP, right? So you can find that kind of paper in IEEE. It's very often the case that people do that.
I missed the parallelization step here. Can you parallelize because it's
Yeah,
Reduce linear arguments. Okay.
Yeah, of course. So like the linearization is a map, right? So you linearize at each time step in parallel, right? And then it's Kalman prefix sum. So this has like a log n log n computational complexity, and its convergence speed is no different from the sequential case, right?
Yeah.
So everything is equivalent.
Yeah.
So, and I think Gauss-Newton has a quadratic convergence rate, if I remember well. Yeah. So like you actually don't need that many steps either.
Yeah.
Okay. Right. So we've been talking about exact, approximate Gaussian approximations, essentially variation methods, right? But can we use that kind of methodology to do exact inference in state space models, specifically MCMC, right? The answer is yes, and it relies on something that is called like auxiliary variable methods. Yeah, that's what I just said. Okay, yeah. So it relies on the auxiliary variable methods. So like let's just do a tiny bit of like background slash refresher on MCMC and the auxiliary variable methods. So if I give you a target distribution pi, you can augment it, right, as pi of x and u, and assuming that it's easy to do, you sample u given x, right? You sample u given x, and that u is acting as a form of localization of your next sample, right? So I say I have x, I just sample something that's close to x, and then I just want to sample x given u, right? And so I've localized my problem. So once I've localized the problem, I can construct an approximation of my target distribution in that domain, right, close to x and close to u. Once I have that, I propose something and I accept or reject, right? No, I mean, our feeling on that? We can do that. Right. So that's a paradigm that's been like used a lot in a paper by Plus. I think I've included in the references, but that is called auxiliary gradient based MCMC samples, right? So the way you typically deal with that kind of problem is by augmenting the target distribution with a Gaussian, right? So pi of ux is pi of x times this Gaussian here, right? Can you see? No, you can't see. Not in the right. Okay. ux, right? And you can also augment it by using gradient information if you want. Make sense? Now the proposal distribution in that case is given as like, well, X, random walk in the first case, if that's what you care about. If you're trying to emulate Mala, then you can see that integrating this distribution according to U recovers Mala, right? It recovers like just the Langevin one-step dynamic. And if you're trying to take Gaussian prior information into account, you just put that in. Right? Okay. And a fairly interesting observation is the proposal distribution does not depend on X. Okay, so like if you have sampled U, then you have independent proposals, which means that you can, for instance, do multi-try CMC at zero cost. Right, it's a fairly nice property. Another version is to just use Mala, but augment by a Gaussian and then use the gradient in the proposal. In that case, you depend on X. So those are more efficient, but because they depend on X, you can't necessarily use those multi-try methods, right? So it's kind of a compromise depending on if you have parallelization or not.
What is the point of using U? Like,
it's a form of localization. So it's saying I want to approximate my target distribution around, right? Because that's how you do MCMC.
Okay.
Let me just use another variable that helps localizing it better.
Try to approximate by everyone. So I try to approximate by him. And also the more credible.
And the thing is, like, once you have sampled U, X given U is very Gaussian.
Okay.
Right? It's always very Gaussian. So it's, at least if you have a Gaussian prior.
Yeah.
So if you're close, like then you're very, very Gaussian in that neighborhood that you're looking at. Additionally on U.
It's kind of a long approximation of the posterior.
Yeah. Yeah. And so, but that's kind of like it's really this idea that like if you look at your target distribution even close to point X, it might not be very Gaussian, right? But once you've introduced that auxiliary variable and you're looking at X given U, it makes it more Gaussian, right? And that's fairly easy to see. It's because that this specific instance, right? This X given U here is going to dominate the actual target, right? For a small delta. So you're kind of like dominating with the auxiliary, dominating with the actual target, and so it's a trade-off between the two. So you make it more Gaussian, but then like you also modify it a bit. In our case, we're lucky because like we're going to be treating of almost Gaussian primes, so it's yeah, it's rather natural.
How does it relate with your work on subgeometric?
There's actually one comment I was going to make, which is maybe clear to many people, but worth making explicit, is you can see the whole thing as an approximate gift set on this trend.
Yeah.
So to some extent, you can use comparison theorems to say, you know, if this Q is a good approximation to the actual conditional, then you're a good approximation to the actual field sample.
Okay. So like the one that we're actually going to be using is that TP, which has like Gaussian priors, right? And so you see like instead of having a proposal that is on the X given U here, you incorporate the Gaussian prior in, right? And so you have some kind of Gaussian, like prior informed proposal. It's kind of like a better version of Crank-Nichols, right? Okay. And so now you just look at your state space model and you assume you have a conditional Gaussian dynamics, right? And so this is essentially a form of, essentially a form of almost Gaussian prior, right? Almost Gaussian prior. And at least if I linearize it, I know it's going to be Gaussian. So I'm going to be doing that. And this is like this potential function that we were dealing with and linearizing to be able to get gradient information. Okay. So if you just look at the TP here, this is like the dynamics, essentially, and this is the likelihood term, kinda. Yeah. So you augment it with the auxiliary observations. So like this auxiliary variable now becomes a form of auxiliary observation, right? In the form of state space model. And once you've done that, you can linearize everybody. Okay. And you say my proposal, given my current trajectory and my set of auxiliary variables that I've been able to sample because it's easy, going to look like that. So I just take my initial time specifier, then I linearize my dynamics around my current trajectory, and conditionally on xk, this is now a state space model, linear Gaussian state space model, right? Well, sorry, those are like linear Gaussian dynamics, and then I linearize my my potential function gamma around my current trajectory. Okay, so here what you can see is the xt's, they don't appear in a big function gamma anymore, right? And so the potential separates across time steps. Like xt, xt plus 1, xt. Even though like the initial version I had was just like a full function. Okay. And so if I'm able to compute those derivatives well easily, then I'm able to form that proposal distribution. Okay. And it's all like in our Gaussian state space models. And so now what you can do is you can say, oh, okay, I'm going to linearize around my current trajectory, right? And use that as a proposal and fit that to MCMC and maybe parallelize everything. Okay. So now you just sample your auxiliary variable, linearize, compute the Kalman filtering with respect to the auxiliary variables and the linearization, sample backwards, compute your acceptance rate, accept, reject, and do that over and over again. Okay. Actually works really well. So, I mean, for the class of problem, it's useful for so like conditionally Gaussian dynamics, SDEs. Yeah. Any remark, comment on that?
I guess just related to what we said the other day, but everything works fine even if you have conditionally Gaussian dynamics that are degenerate in some way, because the Kalman filter doesn't care, you know, only adding noise into the variables.
Yeah, so like if you actually have Gaussian dynamics, not conditionally Gaussian dynamics, then yes, it doesn't care. So if specifically like if that Q matrix here does not depend on xt, then even if you have like hyperelliptic transitions, so like covariances that have like low rank, you're good. Because then like your proposal distribution and your target distribution are not going to be singular with respect to each other. Okay. So yeah, like you'd be good even in that case. And so it's actually a very natural way to do MCMC in those problems, in my opinion. Right. So something that I did allude to, but I don't want to get into it too much. So here, like I've augmented the distribution with that Gaussian UX, but as I was saying, I could have augmented it with the gradient information, and in that case, the proposal would not have depended on my current trajectory. I could have gotten like a ton of samples from my Kalman, right, all in parallel, and then I've done a multiple acceptance step rather than just a single one. And because we are on a GPU, it makes sense, right? Because like the parallelization is actually cheap. Okay. And another thing that enables is to do joint parameter and state proposals. But that's another point. Okay. Okay. So same thing like the. I tend to publish all the code of the papers, but so primitives. I think it's a primitives. No, it's not going to be that. And then Kalman generic. So the way you do it is you say, so that's essentially how you code it. So you sample your auxiliary variables, right? Then you're gonna do one is here. Then you're gonna linearize your dynamics, linearize your observations. There are different ways, like it's that there are more complex ways of forming that proposal, but like linearization is easy to think of. This is just a container for the linear Gaussian state space model, essentially a tuple. You create your filtering. You sample from the full posterior distribution, right? Then you compute the log density of the proposal. You compute the log density of the target, and then like you accept or reject. Right? You just accept or reject. This is just putting everything together to get that acceptance rate. Okay. Once you have done that, you sample your Bernoulli and you keep on going, and you do that in loop. Okay. So same thing, like all those methods, they might look a bit like painful, technical, and computationally hard to implement, but they are not that hard. All right. And say that if you're, they are very hard and very complex, and they're really interesting. Yeah. All right. So some closing remarks on those methods. So we know now how to do parallel inference speeds like filtering, marginal smoothing, or pathway smoothing on linear Gaussian state space models, on finite state space models. We also have seen how like some approximations can be used to get Gaussian approximate posteriors. At least we've done the map. Just be aware that some better solutions exist. As different solutions exist today, different types of approximations. We have seen how to do that, to use that within an MCMC context in a way that is actually fairly scalable and works. If you don't believe me, go see the paper. But what we have not seen is the actual extensions of that. So how you actually minimize the K divergence, but also very importantly, how you manage to get low numerical error in those prefixum operations. So GPUs, I mean, we've been mentioning it earlier. They mostly work with 32 bits precision, right? So like half precision. And Cholesky, you were talking about that. So Cholesky decompositions that you need to be able to do sampling, they tend to be very non-resilient to that. Now, Kalman has the benefit of also having a full Cholesky, square root matrix formulation where you never have to compute Cholesky, but instead you compute QR decompositions. This is way more stable, computationally more intensive, but it doesn't really matter with now context because we parallelize those anyway, right? Yeah, so that's something that I wanted to point out. And so like another thing that I've not really mentioned is how those can also be used in parametric like parameter inference, so doing MLE or that kind of stuff. It's kind of hard to go into details, but because when you do MLE and the gradient ascent or expectation maximization, you end up iterating over either your filtering or your smoothing distribution, then you actually don't want to pay the full sequential cost. And so those methods are specifically useful in those cases when you have to repeat over and over computing the posterior for a different parameter. Okay. Right. So these are like some references, right? So the first one is about like that Cholesky decomposition of Kalman and getting like low error. We have something to do it with prefixums. The second one is the paper by Blaylock about prefixum implementation in general. The third one is about KL minimization for state space model. So like how you find a Gaussian approximation that minimizes your KL. The third one is about the parallelization of HMMs, so the finite state space case, and it's got some Viterbi, so like you can also find the maximum and posterior of HMMs in a longer log time. And the last one is essentially where it all started. Okay. I've not put my papers in there. But I also have a couple in that. Okay, which relate mostly to the Gaussian approximations and the MCMC.
Does the over 3, this works also well with parallel inversion?
Yeah. So like the code I was showing. So some of the code I was showing was essentially was taken from the code of that paper. It's a square root parallel filtering and smoothing, I think, yes. And we have like the general case. We called it square root, but actually it's the whole thing. Okay. Okay. Oh no, I did put them. So yeah, those papers are like 2 of the ones and I didn't put the MCMC one, I think. But yeah, so the 7 is the one with the KL divergence. Okay. The 6 has the Laplace approximation. Okay. I don't know if we want to breather or I'm not sure. I can go on. Okay. And if anyone wants to go to the loo, now is the right time. Right. So now that I've been like doing a bit of advertisement with respect to like a research team that I've been working on, this is something that I actually don't really have any stake in, right? So it's I'm putting it there in between like the Gaussian prefix sum type of thing and the divide and conquer SMC, because it's actually a really nice introduction to the actual problems that arise in SMC, and it uses what we've been doing with prefix sums a tiny bit. So it's a nice kind of in between thing. Right.
I think would it help me to erase the bolts?
I can. All right, so filtering. So Sebastiano gracefully introduced SMC samplers yesterday, and like talked a tiny bit about the resampling step as well, and how like prefix sums can be used to parallelize it, and how some better things can be done. So that's essentially what we're going to be talking about right now. Okay. Yeah, so formal definition, right, of sequential importance sampling. So this does not have the resampling, so it's not SMC just yet. Okay. So you look at a distribution. Where is it? So you want to sample from a distribution pi t. So like on a space that's of increasing dimensions. So you have like a space X, and you're just looking at X to the power t, and you have a distribution over it that's got an increasing dimension. And so the importance sampling method would be saying, okay, so at time 0, I'm going to consider a distribution M node, right? So like an initial distribution, sample from it, and then compute my importance weights. Okay, so samples from M, compute the importance weights. Then at time t, I just look at what I had, right? At the samples I had at time t minus 1. Then I propagate them through a Markov kernel MS, right, MT, and I compute the importance weights that correspond to the new version of my distribution. Okay, and I do that over and over again. Right. Another formulation is to just look at it as a sequence of kernels and product of potential functions. All right, I'm leaving that there for a second. Okay. Okay, now that we have had a second, this is like a classical example. So if you have like your like a standard potential, well, Feynman type of model. So here we have dynamics. Oh my. Here we have dynamics that are non-Markovian, and we have a potential which is non-Markovian. An example would be taking the bootstrap proposals, right? PT. So you propagate according to the density. In that case, the quotients tend to simplify. Okay, you can do it yourself, and the ratios essentially only end up being the ratio of the density in front. So yeah. If you have a Markovian model, right, then it simplifies even further. And I think I didn't write it, but then like you recover the case of a state space model when the G is just like a function of an observation. Okay. So how you would implement that is essentially like that. Sample from, so I didn't put a node. If you have like t equals 0 and xt minus 1, then I just ignore it, ignore xt minus 1. So you sample a bunch of particles at time t, right? Then you compute weights that correspond to the previous weights you had, plus like the increment of your importance density, and you keep on going. You normalize, etc., etc. And then you get like a bunch of weighted particles. The problem with that is as you keep on going, then the weights are gonna collapse, right? So you keep on multiplying things together that are small, right? And so like you are gonna get a form of collapse, not a computational collapse, but a statistical collapse. People tend to think in terms of there's only one particle that's going to be kept alive. I tend to prefer to see it in terms of variance of the weights. It's a choice. And so like you can find that probably in any good particle filtering book. Nicolas Chopin and Omiros Papagiopoulos have one. It's probably in there somewhere. Very likely, actually. And you can show that the weights at time t essentially behave like an exponential, right? And so, sorry, the covariance of the variance of the weights at time t behaves like an exponential. So like the variance of your importance weight goes to infinity really, really fast. Now that's problematic because the variance of the weights is essentially synonymous with the quality of our approximation, right? And so what you do to avoid that is I should look at my slides. Okay. Yeah, so those are the comments I just said. So it grows exponentially, right? And that's true as soon as like your proposal is not your target. Now if you think of the problem, it typically comes from just like keeping trajectories that were not adapted to our problem, instead of discarding them as being just like useless. And we just want to get rid of them as soon as we can. When I say we want to get rid of them, we want to do that in a statistically coherent manner. And so we want something that is asymptotically equivalent. So like something that actually converges to the right target distribution, and also something that gives us unbiased estimator, specifically of expectations, because that's something we use to then get like marginal likelihood, normalizing constant unbiased estimators. Okay, and we do that via resampling. So the formal, there are different perspectives on that, but a formal definition of an unbiased resampling scheme is a distribution of indices that correspond to selecting particles in a way that preserves expectations. So if you look at on the right-hand side, this is your importance weighted distribution, like importance weighted expectation, right? Which corresponds to the empirical distribution of your particles. And on the left-hand side, it's the average expectation of the resampled distribution. So if I resample my particles, I want that in average I get the right solution. Okay. Right. And so examples of doing that are the multinomial distribution, which corresponds to looking at your importance weights, so normalized importance weights, and then saying at index n, I'm just going to draw from the categorical distribution corresponding to my importance sample. Right. And that gives you this type of distribution over your ANs, which are the ancestors of the resampling indices. Another one, which I'm going to be touching upon later again, is the killing resampling, which says with a given probability, I don't touch your index. Otherwise, I just replace it by one of the other ones. Okay, so it's kind of a modification of the multinomial resampling.
One of the other one is uniform, or one of like according to a distribution. When you replace the index.
When you replace, you replace them with those.
Yeah.
Okay. You have like other ones, stratified, systematic, but even though like you can write down the actual density of the ancestor array, it's a bit painful. So I didn't do it, but it's implementable. So another way to think of resampling is to think of it in terms of offspring. So if I tell you you are being replaced, right? What are you being replaced with? Is another particle. Okay, so instead of saying like who is your ancestor, you can ask a particle how many offspring do you have, right? How many descendants do you have? So like how many times were you used as a replacement? Okay. So you just need to count the number of times the ancestors are equal to the particle. So the unbiased resampling perspective can actually be understood probably a bit more easily in terms of offsprings than in terms of ancestors. And so it only requires you, like a sufficient condition, is to just be sure that you have a non-negative number of offsprings. A negative one, I actually don't know what that would mean. The total number of offsprings is exactly the number of particles, right? So like populations, they don't explode or they don't shrink. And then the expected number of offsprings you are is proportional to your importance weights. Okay, and that suffices to have something unbiased. Cool. So now we can replace the sequential importance sampling algorithm we had by a sequential importance resampling algorithm. So whereby instead of carrying over the weights, we look at them, we use them to select ancestors, and we keep on going. Okay, that's what this is doing. So sample, as we did, sample, compute the weights, and then like resample as you go. Fair? Fair? Everyone's familiar with SMC, particle filtering? Yeah? I'm happy to like spend a bit more time because we're going to be doing a bit more of it later. Okay. Okay, so the main question now is how do we sample from those resampling algorithms, right? We essentially look at our empirical distribution, right? And we form its inverse CDF, or like the approximate inverse CDF, right? Like the, it's not a real inverse, a pseudo inverse, is that the term? So we look at the pseudo inverse of the CDF, so like the quantile function. And now if I give you a uniform distribution and you just feed it into your your quantile function, you get a sample, right? It's just this inverse CDF theorem that everybody knows. Now, that's interesting, right? Like all of a sudden we have a perfect sum. Okay, and so we know that we can parallelize prefix sums, right? Because it's just something we've been doing this morning. And so we think that we're going to be able to parallelize resampling, at least like using logarithm n. Okay. Okay. So if you actually want to go from this quantile function to the ancestors, essentially all you need to have is n uniforms, well, n variables that are marginally uniform, right? It doesn't really matter that they are jointly uniform, or like their joint distribution doesn't really matter. It depends on what you're trying to use as a resampling. As long as they're marginally uniform, you'll get something that's unbiased. That's all you need, right? Yeah, that's all you need. Right, and so for instance, the multinomial, which will correspond to the categorical distribution of the weights, you just need to have independent uniforms. For the stratified, you just need same independent well, you need the stratified uniforms, and the systematic, you just need like one uniform, and then you shift everybody through stratas. The killing one, so this is just a mixture of a selection step and of the multinomial. All right, and so if you know how to sample from the multinomial, you know how to sample from the killing. Okay.
So just to clarify what you wrote on that, you mean that each I want to n UI is marginally uniform on 0 and 1.
Yeah, I think that's a question.
I need to think, but being marginally uniform on 0, 1 to the n is a different thing.
Yeah. But you have a changeability, so it's a bit. Yeah, it's probably just poorly written here.
I think for these ones, it's full function.
Yeah. So you like something you use often in SMC is like the exchangeability of the particles. So it doesn't really matter where the first uniform lands in terms of index. It's the representation, like you're only taking sums and averages anyway, so it doesn't matter in which order you're doing it.
The killing is something not really different than the extreme form. The killing is something you have kind of equivalent.
No, but the killing is a mixture, right? No, I don't think so. But it's a mixture of something and multinomial.
Yeah, I mean, for particle that you resample from the killing game, if you want them to be disjoint, so that you have to move to the example.
Yeah.
So otherwise, that way it's not true.
Yeah. Because in the conditional SMC, you would have to be careful, but in the standard one, you don't care.
What's the advantage of killing?
It's very interesting when you have non-informative likelihoods, because what you want is your trajectory not to be broken if you don't need to. Because the multinomial, like even if your particle is valid, it might be then like replaced by another one.
Yeah.
Right, and so your trajectory is jumping.
Yeah.
Right. I was like the killing one, you kind of say, okay, like you're here, you're okay. I want to keep you. Let's not move. Okay. Right. There is a recent paper in I think it was in the Annals of Stats on weakly informative resampling schemes, which actually quantifies that. So you can show that like as potentials become less informative, the solution converges to a LSD, I think, like to some continuous process of some form. Yeah.
The solution of this.
So you put the particle filter over itself into continuous time, and you mentioned, over each small time interval, you do a resampling.
Yeah.
Then there's a certain class of resampling schemes that have a loss time limit, as you said that.
So the killing one, which is an example.
So the killing one is one example of these.
Yeah. And
So the multinomial won't have that property.
Yeah.
The thing is, like, if you jump too much, also you have variance, and so like the whole yeah.
Yes, yes.
Yeah. Okay. Okay. One thing that no, I'll mention it when I use it. So, all right. So we got there. And so like the sequential version of implementing this resampling schemes is you sample a bunch of uniforms, like you have them, and you order them, right? So either you sort them, or you kind of simulate them in an order in the first place. Either way, you pay log n if you're on GPU. If you sort, you pay n log n if you're on the CPU. Okay, so like sorting is log n, by the way, on GPUs. Okay. Right. So you compute your total sum. You normalize the weights, and then here what's happening is essentially you're computing the cumulative sum at the same time as you're trying to kind of find out where the U's end up in the quantiles. Okay. If you wanted to do it, that's not sequentially, it's parallel, sorry. If you wanted to do it in a parallel fashion, you would kind of do it roughly similarly. So you, in that case, you actually don't need them to be ordered, by the way, the uniforms. But so you compute the prefix sum, and then you do in parallel a bunch of binary search, right? So you just say, I've got my uniform, let me try in the middle. If it's bigger than my current cumulative sum, I go to the right, sorry. Otherwise, I go to the left, and I just iterate that. So we know that binary search is logarithmic, right? And so you have something which ends up being logarithmic as long as you have enough threads. Okay. So we're able to do that. Now the problem with doing this is that even though the method is statistically exact, it incurs a computational bias. Okay, so I've lifted that chart from the paper by Murray and friends. And so on the left-hand side, you have this method and the bias it incurs. Okay.
Who is the bias?
Good question. Where is it coming from? Touched upon it today at time. Anyone? Single precision, yes. Single precision and cumulative space. Okay, and so like so the problem comes from the fact that here you're kind of adding small numbers together. Sorry, you're adding small numbers together, right? And so you get into floating point arithmetic issues. And so your particles are not going to be resampled in the right spots. Okay.
So the more particles,
the more particles, the worse it becomes. Okay. And so like that comes from single precision, right? If you had double precision, that would still arise, but later on.
Later on, meaning for much larger.
For much, for larger, yeah. Yeah. Right. And so like seeing that, what we want to do is to kind of like figure out a way to do resampling on GPUs, both like taking advantage of parallelism, and second, trying to avoid computing sums altogether, right? Because if you compute sums, then you end up in that problem. You end up in this situation, and so like even though you might have parallelism, so in practice it should be working, it is not. Okay. So, okay, so what this method does is it reduces the complexity from n to log n. We've seen how, but only for a n that's small enough. Okay. And so yeah, can we get rid of the normalization of the weights of the sums and still pay O of 1 or log n in a sense? Log n is fine. Okay, so if we revisit a bit the multinomial resampling distribution, we see that it's just a target distribution over some ancestors, right? So you have some ancestors, and this is the distribution. Can we sample from it in a way that does not require using the importance weights? The answer is yes. You can do it via Metropolis Excel. And so the way you would typically do it, if you were to like give it a first go, is you would propose an ancestor uniformly, right? And then accept or reject depending on the ratio of the weights. Okay, and you do that over and over again. And if you do it for long enough, it has to convert to the actual target distribution, because I mean, under fairly natural conditions, the weights are going to be connected, and so you don't get you get geometric velocity. Okay. Another way to do that is via rejection sampling. So if you know an upper bound of your weights that you can compute, because finding the maximum of the weights in the array is not the same as computing the sum, it's numerically stable, right? You can then like use rejection sampling. So you propose a given n, a given ancestor, and then you accept or reject it, right? And you do that in parallel for all the possible ancestors you want. Okay. So now, as something you might have seen is here we're starting at an equals n. Okay, so that's like our starting point of our rejection sampling. So it's a question for you: is it unbiased? Because if I was to do it naively, I would just start it uniformly, right? And then keep on going. Good for thought. Right. So it's a rejection sampler. Well, so it's n rejection samplers, right? And those n rejection samplers all have an acceptance probability, which is well, this alpha that I'm writing here. Okay. And so like we know that the rejection sampler termination time is a geometric distribution, right, with a parameter given by the acceptance probability. Okay. So when we look at the actual termination time of the full algorithm, thinking like we have done it in parallel, then it's the order statistics of a geometric distribution, and order statistics of a geometric distribution. Okay. Now, like there's no real closed form solution for it, but you can find upper bounds on the expected time. You can also simulate it if you want. And so once you've done that, you realize that the expected time essentially scales as a logarithm of n. So even though like all the operations you've done are fully parallelizable, you have to go through log n iterations to essentially converge.
Related to this question, Andy asked on the first day about and also with random times.
Yes, yeah. That's essentially what you would have to care about.
What is the variance? It's like at other moments.
The variance. Yeah. So
Variance.
yeah, it's finite. It's finite. It's bigger, but it's finite. There's no real closed form upper bound for it though. It's a bit harder to get. But yeah. There are ways to actually get around that problem, but they require using multiple proposals in the rejection sampler. So in that case, like the probability of acceptance goes to 1, and so you end up with something which is like a very small geometric, so it's okay. And it's actually fairly natural to do it on GPU. Okay. Okay, and so like something I actually also wanted to point at is the other one is an MCMC algorithm, right? And so it's not really clear how long you need to run it for to get into the stationary distribution. Because here, contrary to what you would typically do with MCMC and take like ergodic averages, we want to take the last sample. Okay, and so the question is, if I just look at a single index n, right? I just want to understand the so let's say a. This is like one of the ancestors, and this is now the iteration, right? And I'm going to call pi the distribution of the categorical, right? So I, and I kind of want to understand the total variation between the two in terms of number of iterations of my Markovian, right? The way to do that is just to look at the, so let's forget about it for a second. And this is 1 minus the max of G A equals B for coupling for any coupling between the ancestors. Is anyone not familiar with coupling methods to understand TV distance? It's okay, like we can. Okay. So like the total variation TV is essentially the supremum of all measurable sets of the. Is that an absolute value? I need a 1/2 if I could get it.
Are you doing the sum of the sets? It's just the sets into mu A minus mu A.
Yeah. And if I have the absolute value, it's
the same because you can take the complement later.
And it's also the 1/2 the integral of mu of x dx minus mu of dx. That's the definition of the total variation distance. Okay, and you can actually how to prove that. You can actually feel that if you have two, you have a coupling gamma of mu and mu, right? So something which is a joint distribution over x and y, where x and y have marginals mu and u. Okay, you can show that the probability of x greater than y is always greater than the TV distance. Okay. So no matter what your joint distribution you have over x and y, you have this. Okay. And there also exists one coupling such that this is equal. Okay. But in practice, like you don't really care that it exists. You only care about the fact that you have this inequality, because that also gives you so now you know that if you find the lower bound to that, if you find the coupling for which you have a lower bound, it gives you another bound on the total variation. Okay, and so we want to kind of do something like that. Does it make sense? Yeah. And so now we want to sample from this procedure in two different ways, right? Starting from two different points, and trying like understand the probability of the problem. So if I'm writing A is simulated according to Ki and B is simulated according to Kj, right? So I start B at index J, I start A at index I, and I want to manage to get the A equal B with a positive probability. Okay. The way I do that is I have uniform proposals, right? And so I get the same one. I say C is simulated according to my uniform, 1n, right? And then I only need to kind of understand how I accept it. And well, I accept C as pi of C divided by pi of A, right? And then I pi of I, sorry. Pi of I, and then I pi of C, pi of J. Okay. So now like if I use the same uniform for both, right? I know that I'm going to have A equals B, as soon as my uniform is less than the minimum of those two. So alpha I and alpha j, right? Minimum of alpha I and alpha j. As soon as I have that, then I'm good. Now, what's the probability of this? This is the probability of it. Okay, and so now I know that I've done that for C that was distributed uniformly, right? And so I know that the total probability is the sum for all possible C's. This depends on C, right? The sum for all possible C's of this. Make sense? Okay. And now I just need to lower bound that. And you can see fairly fast that the lower bound is given by taking the maximum of the weights. Okay, and forgetting about 1, because now that's going to be that 1. And so I've got 1 divided by n, and then the sum of the wj's divided by the biggest. Okay, and I call this beta, right? And now I know that I have so k I k j is less than 1 minus beta. Okay. So if I start j at its stationary distribution, right? Because k is prime invariant, like categorical invariant, then I also want it. Okay, and now I can iterate my kernel n times, right? And that's all I get. Okay, and so now if I want my total variation started at any point to be less than a given epsilon, right? Then all I need to find out is n equals log epsilon divided by 1. Okay, so I need to iterate my MCMC.
I think it's the complication. The good beta is small things about. Everything else is fine. It's just the n that you need to make it small should be more like log 1 over epsilon divided by beta.
So
Yeah.
nice. Right. And so now we look at beta, and then we try to say what is a lower bound on beta, because that gives us an upper bound of steps. And you can see very easily that this is a lower bound. Right.
That's quite nice. One of the rare occasions where you exactly know how many MCs you stand there.
That's all right. Okay. Yeah. So you actually get a solution, and if in fact instead of going and lower bounding beta by 1 over n, you can find the estimate of that, right? And that gives you maybe like a more empirical way of understanding how you do it. Okay.
And that's a practical statement.
That's a practical statement. Yeah. Yeah. That's a yeah. If you want something robust, you do 1 over n. If you want to kind of like have an adaptive version, you. All right. And so like what you end up with is essentially a method that scales better. right, and doesn't have bias, even though the method is biased. So like the Metropolis method is biased, you have an epsilon bias. But in practice, because you don't have the numerical error, it works better. Yeah, it's surprising, right? A bit. So like the unbiased method works worse than the biased method because of the numerical issues. Okay.
Something like the number of steps that we thought was supposed to be run. Like log in. Okay. Yes, yeah. That's just a sort of related thing. I have a list of n floats, and I have parallels of variables, and I want to sort that list.
That's logarithmic.
That's okay.
Sorting is logarithmic, yes. Yeah, it uses merge, so it's a form of merging, and you can parallelize all it. Okay. Yeah, so I guess after the break, I'm taking longer than I expected, actually. Yeah. Yeah. So after the break, what I wanted to talk about was how you extend all that. So this is like stuff that's in the paper, but it's actually pretty fun to kind of try and think how you'd extend it to other eccentric schemes and how you would, for example, make the MCMC version exact, right? We can skip depending on, yeah. I mean, it's kind of depends. Yeah, I'm not sure. Like, should we do the SMC first and then like come back to that one if we have time? Like, or do we have a lot of time today? I'm not sure.
It's up to you, really.
It depends. Are people liking it? So that's the. So we can spend a bit of time with bio sampling still. It depends how much people have an interest in it.
Yeah.
Yeah.
Yeah. All right. Lunchtime, guys. Thanks, Robert. Football, yeah. Today's proper food. Today's proper food is hot food, so sandwiches. Which is officially less expensive than sandwiches, I'm told.